Problem 10 on 7.2.
Integral of x squared times arctangent of 5x.
I'm sorry, this one, the arctangent is out. What are we taking the arctangent of here?
What was the arctangent though? I just. What was the arctangent?
Oh, 5x.
5x.
You don't need some. Music theory is extremely difficult.
So other than the fact that this comes from section 7.2, what's the dead giveaway that this is an integration by parts problem? Multiplication, and it's got inverse trig function in here, right? If you've got an arctangent as part of your integral and you don't have a 1 plus x squared in the bottom, then that makes it not an ordinary UDU integral. But if you see a logarithm or an inverse trig function, I want you to think in terms of integration by parts. The product is also a giveaway that it's integration by parts. And since we don't have an integral of the arctangent, we pick the U term to be that second one. And that leaves dv to be the x squared term. So we take the derivative of the u and the integral of the dv. All right, what's the derivative of the arctangent of 5x?
5 over 1 plus 25x squared.
All right, so it's 1 over the variable squared, but then we take the derivative of that and it gives us that extra 5. Over here, we're integrating. So we're going to get x cubed over 3. We good so far? Okay, now we got our integration by parts scheme. We're going to take u times v minus the integral of v times du. So here's my u times the v. I'm going to go ahead and put the x cubed over 3 in front of the arctangent of 5x. Now we have v times du. So my v times my du. We'll go ahead and write that as 25x squared here. So before you attempt anything with the second integral, let's simplify it as much as we can. Like that 5 on top and the 3 on the bottom can come out in front of the integral as a 5/3. And then I can slide the x cubed to the top. Here's that first part of our antiderivative. And then I want to take the 5/3 out front and put the x cubed on the top. And the resulting integral has a fraction where the degree on top is more than the degree on the bottom. What does that tell you you can do? You can divide. You can divide the bottom into the top. So now there are other ways around that. Right, I can try a Ddu substitution, it'd be a double substitution. But I'm gonna go ahead and do the dividing just because. I'm gonna rewrite this in descending order as 25x squared plus 1. Then we're dividing that into x cubed. So I know I'm gonna need an x, but I'm also gonna need something to get rid of this 25 here. So what am I gonna write as my quotient term?
125.
1 over 25 times x. Now I'm going to multiply both of these by that. When I multiply 1 over 25 times x with 25x squared, that's how I get the x cubed. But then I'm also going to get plus 1 times 1 over 25 times x. And then you subtract that line from the line above it. I'm not seeing that. Just an inch. And when I subtract the x cubes, subtract each other out, and I have a negative 1 over 25x. That's going to be my remainder term because it is already a degree smaller than my divisor. So this is the quotient. We write our fraction as quotient plus the remainder over the divisor. There's the divisor, and there's the remainder. So my quotient was 1 over 25x plus the remainder, negative 1 over 25x over the divisor.
Thank you.
Okay. Now we got two integrals to do. The first integral, we just get 125 times x squared over 2. Then it's multiplied by the 5/3. I'm going to distribute the minus 5/3 to this second integral and combine it with the minus 1 over 25. So when I take this and multiply it with that, a negative times a negative gives me a positive. Can you simplify 5/3 times 1 over 25?
1 over 15.
1 over 15, is that okay with everybody? That times that is going to give me a 1 over 15 right here. Then I'm going to leave the x inside the integral. We've got to do that integral next. Oh, I forgot to integrate that. There we go. Thank you for catching that. So that third integral there, what's that? What's the way we're going to do this integral?
UDU.
UDU. That's an x squared. That's an x to the first. That'll be an ordinary UDU integral. So here we take u, the 1 over, I'm sorry, not 1 over, we just take the denominator. Du is going to give me 50x dx. So the x dx is a 1 over 50 times du. We're going to take it over here. So I'm going to copy this down, and then the UDU substitution. And we've got x cubed over 3 times the arctangent of 5x. I'm going to simplify that to a minus 1 over 15, minus 1 over 30 x squared. Then I've got 1 over 15 times 1 over 50. I don't think I can do that arithmetic, so I'm just going to write that. And my integral is 1 over u du.
That's 750.
I would take your word on that. They'll say that's a 750. I did so many numbers in my calculus 1 class this morning, I can't do numbers anymore. That is not in my job title. Integral 1 over u,
And then you,
natural log of u, and then we're done. X cubed over 3, arctangent of 5x, minus x squared over 2, oops, sorry, 30, plus 1 over 750, natural log of u, but let's go ahead and fetch the u. 1 plus 25x squared. Plus c. Wow,
That's not one. I've got another one.
you've got another one?
Uh-huh.
Let me make sure everybody has a chance to write this one down. 'Cause I went there to there. Yes,
So in integration by parts, the u is always the. So, like, we don't know the score of the.
right. Right, usually I pick the DV first, which is the largest part I can integrate. And there was only one part that I could integrate in my, of these two choices. The only part I knew how to integrate was the x squared. So you got that written down? I'm hitting your race. All right, tell me your problem, then I'll erase while everybody writes it down. What's the problem I'm doing?
X cubed over X.
All right, let's get it started. What makes this an integration by parts?
polynomial times log.
A logarithm and a polynomial. So again, here we've got our decision made for us. We don't know how to integrate the logarithm by itself. So the polynomial has to be the DV. So the polynomial has to be DV. That leaves u to be the natural log of x. Take the derivative of the u, you take the antiderivative of the dv. So the derivative log of x is 1 over x. So when you integrate here, you add 1 to the power, divide by the new power. Now we're going to write it out in terms of uv minus the integral of v du. Let me first write the formula. U times v is the log of x times x to the 4th over 4. And there's the log of x, there's the x to the 4th over 4. Minus the integral of v times du. Oops, I labeled it wrong. That's du. So v times du is 1 over x times x to the 4th over 4 times the dx. Always, always, always simplify that resulting integral before you try anything on it. So we can simplify by pulling this 4 out as a 1/4. This x divides into that, leaving me an x cubed. Okay. Then the integral of the x cubed here at the end is going to be an x to the 4th over 4. How's that? More? Okay.
The integral of 5x cubed times e to the negative x squared.
Okay. Now, if this were just e to the negative x, then I would try integrating this in table form. But since it's an e to the negative x cubed squared, sorry, e to the negative x squared, I don't know how to integrate that. You're going to integrate an e to the negative x squared, you need its derivative to appear in the integral somewhere. So you'd need an x to the first power. Well, we do have an x to the first power, it's just hidden in here. So I'm going to break this up into 2 terms in this way. I'm going to write that as (5x squared) as one term, and then x e to the negative x squared as the other term. Why did I do that? So now we can integrate this, right? So now this is my dv. And this is going to be my u. In order to get the dv, we've got to do some scribbling in the margin over there. Okay, so we're going to pick u to be the 5x squared, and dv to be the x e to the negative x squared dx. And then to do this integral here, we got to do a little bit of work. I'll just do it right here. I'm going to integrate x e to the negative x squared dx by substitution. But I'm not going to do u du because I got my u over there. So grab another letter of the alphabet.
A.
T, T. Let's use a T. I'm going to let T be negative x squared so that dt is negative 2x dx. That's this x dx. So for that x dx, I'm going to put in a negative 1/2 dt to be the x dx. So my v term is the integral of e to the t times 1/2 dt. What's the integral of e to the t? Or in this case, t is x squared. So we get 1/2, negative 1/2, sorry, negative 1/2 e to the t, but t was a negative x squared. So that's my v. Then our du is 10x dx. Pull it back over here. Okay, I can scoot that over. So there are going to be times where you can't go from dv to v in your head. So don't be shy. Just write out the steps to integrate. Okay, now we're ready to integrate by parts. So this integral here is equal to u times v minus the integral of v du. So my u was the 5x squared. It took a while, but we got v to be negative 1/2 e to the negative x squared. Minus the integral of v, okay, there's my negative 1/2 e to the negative x squared again, times du is 10x dx. Make sure you know where everything comes from before I write the next line. Okay, again. uv minus the integral of v du. We've got to simplify the v du integral. I can take half of 10 and get 5. Pull that out front, I got two negatives. Let's go ahead and put these two together and write that as that one. Write that as a negative 5/2 x squared e to the negative x squared. Then I got a minus to give me a plus. Half of 10 gives me 5. And let me put this in the order of x e to the negative x squared dx. But we did that integral. We did that integral right here. So we know that second integral is going to come out as a negative 1/2 e to the negative x squared. So here's our final answer. Negative 5/2 x squared e to the negative x squared plus 5. Again, from the bottom left-hand corner, negative 1/2 e to the negative x squared. Is that a good problem or what? Say it again, please.
What do you know?
By practice. Like I said, if that wasn't an x squared and the exponent on the e, then I know I could do a table. But because of that x squared, I knew I had to do some finagling like I did over here. And that no longer was going to be repetitive calculations. So maybe don't use the table, maybe just do integration by parts, and then after a while, you'll see which ones are repetitive. Another one? All good? Okay. Then today we're going to look at section 7.3. The first part is integrating varieties of trig functions put together. We're going to break it into 3 categories: integrating cosines and sines as a product in an integral, integrating secants and tangents, and then the other pair that goes together would be cosecants and cotangents. We're looking at varieties of trig integrals. Nothing's going on well with the black ones. So from part one, the first type of integrals we're going to consider is integrating sine to a power times cosine to a power. And armed with the knowledge that the derivative of a sine is a cosine, and the derivative of a cosine is minus the sine, if any one of those two powers is an odd power, I'm going to try to do a Ddu substitution. If either m or n is odd, grab a factor from the odd power and put it with the dx term. Pull out, whichever one has the odd power, pull one of those out and pair it with the dx term. So for instance, if this was an odd power and cosine, I take one cosine out of there, which now leaves me an even power on cosine, and I have a cosine of x dx. So then I would want to write the rest of my integral in terms of the other trig function. So if I'm pulling a cosine out and have an even cosine left, I have a Pythagorean identity that changes those even cosines into sines. So then use that cosine squared of x is 1 minus sine squared of x, or sine squared of x is 1 minus cosine squared of x, and write the rest of the integral in terms of the other trig function. Once you do those two steps, you've got a Ddu integral. So that's the easiest case. If one of the powers or both of the powers are odd, pull an odd one out, write a Ddu integral. So here's one where they're both odd. They're both odd powers. As soon as I saw an odd number, I said, I got me a Ddu integral. I have my choice. I can pull out a sine of x, or I can pull out a cosine of x. I'm going to pull it out from the lower one just because I'm lazy. I know my subsequent steps will involve squaring. So I'm going to pull a cosine of x out. I'm going to rewrite that as the sine to the 7th, cosine to the 4th, and then cosine of x dx. So this is what I mean. I'm setting this up as the du. If that's du, all of this has to be in terms of sine. So I'm going to replace cosine to the fourth with cosine squared squared. Where cosine squared is 1 minus sine squared. So that's why I chose the lower power. Because after I do a Ddu substitution, I've got a binomial I need to square. So now's a good time to go ahead and make the Ddu substitution. Just take u to be the sine of x. Leave behind all the powers. Take u to be the sine of x. And then du is the cosine of x dx. My trig integral becomes a polynomial integral. So this integral becomes u to the 7th, 1 minus u squared squared times du. So square it, combine terms, we're going to spread it out all the way, and then we'll be able to integrate it. Pull it up here. I got to square the 1 minus u squared, and I get 1 minus 2u squared plus u to the 4th. Then I got to send the u to the 7th through the parentheses. Keep going across the top of the board. And I got u to the 7th minus 2u to the 9th plus u to the 11th du. Got rid of the product. Now I just integrate term by term with the power rule. Keep going across the top of the board. We get u to the 8th over 8 minus 2u to the 10th over 10 plus u to the 12th over 12. And each u is now a sine of x. So our final answer is the sine to the 8th of x over 8. Let's write that as a fifth. So next one is sine to the 10th power of x over 5 plus the sine to the 12th power of x over 12. One or both of them is odd, that odd feller has a du term hiding in it. Pull one of those odd ones out, the rest are even. We can always substitute out even powers of sines or cosines with a Pythagorean identity. So the next one I want you to do is integrate sine cubed of x. Find for me the integral of sine cubed. It's going to work the exact same way. Pulling one of them out to serve as a du. If a sine is a du, the rest has to be cosines. That's where your Pythagorean identity comes in. Take the rest cosines using the Pythagorean identity. to be the TU. So you got to get rid of the sine squared that's part of your integral. Sine squared is 1 minus cosine squared. Now you have it set up as a u du integral. Take u to be the cosine, du is minus the sine. So you're going to get minus this integral. 1 minus u squared times du. Easy schmeezy, right? Break 1 minus u squared and get u minus u cubed over 3. So let's go ahead and distribute the minus sign and write that backwards as u cubed over 3 minus u. And each u was the cosine of x. So our final answer is the cosine cubed of x over 3 minus the cosine of x plus our arbitrary constant. So everything we do today, that's the easiest case. An odd power is on a sine or on a cosine or both. Move one first degree out as the du term, write everything else in terms of the other trig function using the Pythagorean identity. Okay, the second case is the messier case if both of the powers are even on sines and cosines. Then we've got to use that same power reduction formula that we used when we integrated a sine squared, and the power reduction formula that we integrated for cosine squared. Our second case. M and N are even. We use the facts or the identities that you can replace a sine squared with a 1 minus cosine of 2x over 2. And you replace a cosine squared with a 1 plus cosine 2x over 2. Then you'll have to do the algebra and see what happens next. Should I do the easy one or should I do a harder one? No, we don't have time. I'm just going to do a product of sine squared with cosine squared. So I don't have the option of pulling out a sine or a cosine, because once I pull out a sine or a cosine, the Pythagorean identity doesn't fit anymore. So I'm going to use my power reduction formulas for each of these. Replace every single even power trig function. I'm going to put that in where the sine squared is. I'm going to put that in where the cosine squared is. Then we got to multiply it out. So that's why I didn't put any 4s up here, because I didn't want to have to multiply something to the second power and then another power. So when I multiply the 2's together, I get a 1/4 out front. Then I have 1 minus the cosine of 2x times 1 plus the cosine of 2x. What does that product yield? Other way, do 1 minus the cosine squared of 2x. Now I can integrate each of those, or I could use a Pythagorean identity, whichever I prefer. I know how to integrate one, I know how to integrate the cosine squared. I'm going to go ahead and use a Pythagorean identity, so I just have one integral to do. 1 minus cosine squared is sine squared. So 1 minus cosine squared of 2x is equal to the sine squared of 2x. But be careful, I've got a multiple angle, so I'm going to do a Ddu substitution. I'll take u to be 2x. Du is 2 times dx. So 1/2 du is dx. Take that 1/2, multiply with the 1/4 and get 1/8. And then we're left to integrate sine squared of u. We have a formula for that from back in chapter 6. Everybody still remember it? Okay, then we'll use u's. Where each u is 2x. Okay? So if I'm integrating cosine to the 4th by itself, I write cosine to the 4th as cosine squared squared. And then I put that in for the cosine squared, multiply it out, and I now have lesser degree. And I can integrate term by term. Okay? So both are even, or if you just have one trig function to an even power, these power reduction formulas are going to replace the square of that trig function. Then you're going to have the other power on it, so you'll have to expand it. And hopefully once you expand it, you have something lower degree that you know how to integrate. Okay? Okay, so those are the easy ones, because sine, root of sine is cosine, root of cosine, sine squared plus cosine squared is 1. Now we start mixing up tangents and secants. What's the derivative of a tangent? Derivative of a tangent is a secant squared. What's the derivative of a secant?
Secant tangent.
Secant tangent. And what does the Pythagorean identity look like in terms of tangents and secants? Tangent squared plus 1 is secant squared. Armed with that knowledge, now we can integrate powers of tangents and secants. So let's write down the knowledge again. So now we're looking at integrals of this type. We have tangent to a power times secant to a power. It's not going to be as cut and dry as it was for sines and cosines. It's a little bit more thinking to do. The thinking that you're going to do it is that u is equal to the tangent, and du has to be a secant squared. Or, our other choice, if u is equal to a secant, then du is secant times tangent. So if I pull out a secant tangent, the rest of the integral has to be written in terms of secant. If I pull out a secant squared, the rest of the integral has to be in terms of a tangent. And our relationship has squares on them. Tangent squared plus 1 is equal to secant squared. So if you're going to pull out a secant squared and need to write everything else in terms of tangent, you have to have some even powers of secants left behind. Or if you pull out a secant tangent, you've got to have some even powers of tangents left behind. And then hopefully you have a UDU integral somewhere. Let's try this one. Anybody see anything you can use here? Don't need to pull anything out. We got a secant squared in there. Just take u to be tangent, du is secant squared. It's already a UDU integral. Right? It's already a UDU integral. The derivative of tangent is secant squared. So just take u to be tangent, not tangent cubed, just tangent, and du is secant squared. We're done. We're integrating u cubed du. So that's our motivation and what we're thinking about. Is the derivative of one function part of the integral? If it is, u du. If it's not, make a plan. So if I had something similar, just change the power on the secant squared to a secant to the 4th. Knowing how easy that last example was, what do you want to do? Pull out a secant squared. But the important thing is a secant squared is left behind. And I can get rid of the secant squared and write it in terms of a tangent. And then I have the same problem back again. Pull out a secant squared. So you're kind of working backwards. If that's going to be my du, all of that has to be a tangent. So I needed to have an even power here. That even power allows me to use this. And now you have a UDU integral. You're pulling out a secant squared. Can you write everything else in terms of tangents? That's what you're asking yourself. So here you take u to be tangent, and du is secant squared. So you have u cubed times u squared plus 1 times du. Pull it out, integrate, and you're done. Tangent to the 6th of x over 6 plus tangent to the 4th x over 4 plus c. So what you needed in order for this to work is if the power on secant is even, pull out a secant squared. If the power on secant is even, who cares what the power on tangent is? If secant has an even power, pull out a secant squared. and then let u be the tangent. Got u in it. So you would almost bet that if the power on secant is odd, pull out a secant tangent. And the answer is sometimes. But that you're pretty much right. Okay, we have a student wellness day on Friday, so we have no classes, not even a Zoom class. You're off. I want you to concentrate on being well and doing some web work. I don't think this web work's due for a while. And this one? I'll fix it.
7-2.
7.3 I just put up this morning, I think. So I think I gave you about a week to do that. So you probably have enough just to dip your toe into 7.3 right now. Because there's so much more that I haven't covered. So take it and go and look at Blackboard and see which assignments you've missed turning in and turn them in to me. I'll take them late. Just turn your stuff in so I can start filling in the little squares. Thank you. Thank you very much. Then you will see your tangent. Because then you're going to try to do a UDU in this one.
Right, okay, so the secant is even, you is and if the tangent is here.
We always look at the secant. Always look at the secant. Oh, thank you. Okay.
So here.
We'll make sure these guys are okay here. Let's see, I got a chat thing here. Thank you, Mia. Okay, so we're done.